Aziz Omar, and also to my fellow friends. Unfortunately, right now my supervisor might be late, so I proceed first. Today I will be presenting my final year project 2, and the title is Accidental Nanoparticle Factors Affected to the Dispersal Behavior Produced by Engineered Nanomaterials. From this title, I want to highlight two things. First is the accidental nanoparticle factor, and the other thing is how it affects the dispersion behavior. And I will explain this further during the discussion. Okay, this is the outline of my presentation. First, I will be introducing about project background, literature review, methodology, result and discussion, and last I will conclude all. Okay, for the project background, nanoparticle can be defined as the particle typically within the range of 1 to 100 nanometer. And the nanoparticle, it has a different size, can be spherical, tubular, or even irregular shape, and they can exist in fused, aggregated, or agglomerated form. And the nanoparticle, they can compose of organic materials, either natural, synthetic, or even metals. And what makes it more different from micro is the fact that it is large surface area, thus it has the higher reactive surface area. And here from this figure you can see the range of the size between 100 million to 0.1 nanometer. So nanoparticle can see from this figure, it's between the glucose and virus. Nanoparticle has a very wide application in industry. It can be ranging from textile, medical, pharmaceutical, and more recently in cosmetics. Okay, before this, from this title, I highlight the accidental nanoparticle factor. The accidental nanoparticle factor here is the fire and explosion. So when we talk about fire and explosion, one of the parameters is the explosion severity. And this three is the explosion severity parameter that I want to investigate in this project. First is the overpressure, Vmax, and overpressure is the maximum explosion overpressure recorded by the equipment. And the rate of pressure rise is the maximum rate of pressure rise, so this indicates how fast the explosion is occurring. And next is maximum normalized rate of pressure rise, KST. This is also known as explosion severity index. From this value, it provides an indication of how severe is the explosion, and the larger the value, the more severe is the explosion. Okay, the problem right now, the fire and explosion hazard associated with nanopowder is not fully explored yet. And the dust explosion research involving nanoparticle is very limited, whereby most of the research only covers the micron range. And they also encountered some problem. And due to this, some researchers, they concluded that the explosion severity follows the cubic relation, which I will show in the discussion. From the cubic relation, they state that as the particle size decreases, the explosion will decrease as well. The objective of this project, first I want to investigate the explosion severity of the carbon nanofiber and also the multi-wall carbon nanotube. And then I will compare this data from the one found from literature review and also compare it with the carbon micro-sized carbon material like coals. And also, last but not least, I want to see the thermodynamic relation of the combustion of carbon. The scope of this project, the material that I use is carbon nanofiber and multi-wall carbon nanotube because it is widely used in the industry, and also it is very available. For my project, I will cover the experimental part, while my other friend Koyung will cover the simulation part. For this experiment, I will be using a standard 20-liter spherical explosion test system, which is installed in the block form. Okay, this is from the literature review. Based on the findings, you can see that from 2011, is what they say. The explosion severity follows the cubic relation, whereby the severity increase with nanopowder. However, Boylard says that the nanotitanium is more sensitive although the severity is quite comparable to the one from micron and nano. And recently, it shows that the explosion severity shows a plateau, a bit of a plateau. And one of the possible problems that they encounter right now is the pre-ignition. And he concluded that if you want to extrapolate data for nanoparticle using equivalation, it is not valid for nanopowder. And this is what I meant when I say plateau. So the plateau can be seen from here. So when you go from 100 to 0.01 micron, so it's from the range of micron to nano, you can see that the KST is increasing at first, and then there comes a plateau whereby it will decrease. So the final value is comparable to the micron, and also the same for the Pmax. Okay, the properties of the carbonaceous nanomaterial. For my project, I use carbon nanofiber and also multi-wall carbon nanotube. And here you can see the difference between carbon nanofiber and carbon fiber. You can see the structures is different, and also the diameter is. And next is the single wall carbon nanotube and multi-wall carbon nanotube. The difference is how much layer is there. Single wall carbon nanotube only have a single layer, while multi-wall has multiple layers. So single wall is much more expensive. You can see from the diameter is different, which single wall has the finest diameter. The aspect ratio is also different. And one of the main application of this carbon is in the micro electronic parts. So that's why the thermal conductivity, the electrical resistivity is very important for the carbon nanomaterial. For the methodology part, first what I do is to find the current limitation based on the literature review, and then I want to determine what type of material that I want to use. And also, next is to conduct the dust explosion experiment and data gathering and data analyzing. This is the specification of the material that I use. For carbon nanofiber, the diameter is around 200 nanometer, while the multi-wall carbon nanotube is around 20 nanometer. 20 nanometer is actually very strong, very small. And this is the equipment that I use. This is the standard 20-liter spherical explosion test system. Most of this figure is the schematic diagram, while this is the actual equipment installed in block 4. Based on my experiment, I obtained the pressure time curve for carbon nanofiber. From this pressure time curve, you can see Pmax, the KST, and also the rate of pressure rise. And this is how intense the explosion really is. And the explosion only took about 1.5 seconds. And this is the pressure time curve for multi-wall carbon nanotube. And you can see the Pmax and the KST is much higher compared to the previous one. And this is the explosion intensity. So you can see for multi-wall carbon nanotube is much more intense. The explosion is has higher pressure. And I also conducted experiment for hydrogen gas as a means to compare it with the carbon nanomaterial, because some researchers they claim that if a particle is very fine, particularly ranging between 20 nanometer and below, it can behave like a gas. So that's why I conduct for hydrogen gas for the sake of comparing the data. Okay, this is the summary of the results. You can see here the Pmax is for multi-wall carbon nanotube is much higher, and when we compare between CNF and multi-wall carbon nanotube, the Pmax and KST increased by 30% and 13% respectively, although the velocity decreased by 12%. But when we compare it to hydrogen gas, especially for multi-wall carbon nanotube, we can see that it is not much different. So from my project, I concluded that for the material 20 nanometer diameter, it can be compared to the hydrogen gas. So from my result, it is shown that the explosion severity is comparable to the coals and carbon blacks. The range is between the range, and the explosion overpressure and the explosion severity index for KST for the multi-wall carbon nanotube, the data is comparable to the one from Boylan, which did the same experiment as me, but he didn't use the carbon nanofiber. And it can be said that the carbonaceous nanomaterial fall in standard 1 band of explosion severity. The band of explosion severity, they have 3 bands: standard 1, standard 2, standard 3. With standard 3 is the most severe. So you can say that for carbonaceous nanomaterial, it's not much severe. And the characteristic velocity of the explosion front, which are around 8 meter per second, is comparable to the one from the coals of Pocahontas, which is a Pittsburgh standard based on cash dollar papers. And this research showed that the explosion severity of CNF and multi-wall carbon nanotube is comparable to the hydrogen gas. And this also supports the theory that as the particle size decrease from micro to nano size, the explosion severity is still very much comparable. And this rejects the old notions that the explosion severity for nanoparticle follows this type of cubic relation, whereby the explosion severity will increase with decreasing particle size. And some possible explanation why the explosion severity is comparable is because of the particle agglomeration, the wall quenching effect, increased oxide content, and pre-ignition. Particle agglomeration here happens when we have a nanoparticle in bulk quantity. So then the particle will agglomerate. Wall quenching effect is basically the heat loss to the wall, and the increased oxide content is the increase in the oxide layer of the particle. Pre-ignition is one of the main concern, but for my carbon nanotube and also for the carbon nanofiber, I didn't see any pre-ignition of material. However, based on the literature review, they found out that for titanium and chromium, it experienced pre-ignition of material. Pre-ignition here means that the material ignite without having ignition source. So when you release it and disperse it, it will automatically ignite. And this these 4 factors might underestimate our data, might underestimate or even worse, and overestimate. Next, I want to see the thermodynamic relation. First, we want to consider as stoichiometry, and whereby we found out that all of the oxygen in this test chamber react with enough carbon, and then it yields carbon monoxide, and releasing the heat based on this equation. And also the delta H, later on, the heat heats up the gas with temperature increase, delta T equal to delta H over CV. CV here is the heat capacity of the gas, and heat capacity of the gas for this experiment is considered to be the heat capacity of the air, the mixture of air and also the oxygen. From this relation, I come up with the overpressure, which is given by this equation. However, this equation only true when it is at stoichiometry, when the reaction is at equivalent. However, when we go above stoichiometry, we have to consider also the alpha. Alpha here means that how far you go above the stoichiometry. So alpha must be bigger than 1. So this is the relation. After above, when we go above the stoichiometry, and thus using the relation we can estimate the Pmax. Last but not least, from this project I concluded that the explosion severity of carbon nanofiber and multi-wall carbon nanotube were found to be comparable to coals and also to hydrogen gas. And this is mainly caused by the particle agglomeration, wall quenching effect, increase in oxide content, or even pre-ignition. But for my part, I didn't observe any pre-ignition. And also, the thermodynamic relation was developed with reference to Turkovic in his paper, whereby we want to estimate the Pmax using this relation. For recommendation, for future work, I want to recommend to conduct the experiment on the explosion sensitivity. Basically, if you want to conduct the explosion experiment, you have to consider two parts. First is the explosion severity. The second is the explosion sensitivity. Explosion severity here is how severe is your explosion, and also how much pressure is generated based on your explosion. For explosion sensitivity, we want to see how sensitive it is, how easily it is to be ignited. And the parameter is the minimum explosible concentration, minimum ignition energy, minimum ignition temperature, and limiting oxygen concentration. Minimum explosible concentration is the minimum amount of material, the minimum concentration of material that is used for the explosion to occur. And the minimum ignition energy is the minimum energy that is required to ignite the material. The same goes for the MIT, minimum ignition temperature. And the limiting oxygen concentration here is the amount of oxygen that will limit the explosion to occur. And also, I want to recommend the experiment to be conducted on different level of concentration and size of particle, because due to this limitation of budget and also the material that I have, I only considered a same concentration of material, but I run it in two different, I repeat it. But what I want to recommend is for future work is to have a very different set of concentration and also a different size of particle, so you can further compare it. And also to study on the possible effect of particle agglomeration. Particle agglomeration here happens when you have a nanoparticle in a bulk quantity. So when you have it in a bulk quantity, it will form a cluster. So a bit like the cluster form will have a bigger diameter than the original nanoparticle, so that when you release it, it will behave like the larger particle, not like the nanoparticle. And some of the paper, they found out that the particle agglomeration can be as big as micron. They use a nanoparticle, but because of the particle agglomeration, the agglomeration size can reach to micron. So when they release it, it can behave like micron nanopowder, micron powder. So that's why they hypothesize that it might be the factor why the explosion severity for nanoparticle is comparable to the one from micron size. And last but not least is to conduct the test on different materials, so you can see more the relation and also to prove the theory. Okay, thank you. Question and answer session.
Okay, thank you, Ariffin. Simple work. Simple. And dangerous one. What is why do you study this explosion severity of nanoparticle? What's the danger from this nanoparticle? Why you study this? Very simple question.
Because as far as the data goes for dust explosion, it only covers the micron. So from the micron size, you can see it has a tendency to form dust, and when it disperses, it will form explosion followed by fire. So for nanoparticle, they concluded at first that it's much more severe than micron. So right now, the industry is using nanoparticle in wide range. So the data on the explosion hazard is not very known, and also the regulation does not cover the nanoparticle yet. So the severity of this nanoparticle is not yet known. So that's why we want to conduct this experiment. But based from my reading on the literature, they found out that although the severity is comparable to the micron, but it is more sensitive to explosion. And the minimum ignition energy is found out to be less than 1 microjoule. So you can imagine how low is the energy. So you can consider that the nanoparticle, when they form enough concentration, when they have enough concentration, you can easily ignite it with the spark of a spark plug from a car. So let's say you have a plant, and your plant is using nano powder, and then accidentally you didn't handle the nanoparticle well, whereby you store it in not in an inert condition, so it will be agglomerate, and then if you have a source of dispersion, it will disperse, and then if a car goes around, the ignition of the spark plug can cause the ignition of this the cloud. So the explosion is very easily to occur. However, the severity is comparable to the micron. So the problem right now is the explosion data for nanoparticle is very limited. So that's why this project is very important for the future.
You write all those things in your introduction?